In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most All
right, hello and welcome everyone.
What's up, man?
Cheers.
What up?
Yeah, we hear you.
Yo,
Welcome.
thank you. Cool. So during the presentation tonight, if anyone has any questions or comments in between slides, we can definitely get into it for clarification, but this is a rather lengthy Prezi. I did an uninterrupted version on EtherCause earlier in the week, and it ran 2 hours. I'll see if I can trim some of that time down. But if we reach like a stalemate or impasse or something like that, we can come back to it. But yeah, if anyone has any questions though, feel free to ask. No worries. So we'll go ahead and get into it. All right.
Sounds good. Yep, I've I've got it shared on the live stream on this end too, and yeah, everything looks good. So cheers. Looking forward to it. I'm glad you're here.
Fantastic. Thank you, sir. All right. First of all, shout out to Earth Awakenings. Awesome host and always holding it down, facilitating the conversation of cosmologies and differing opinions. So shout out to the boys over here. Now what I have is a null hypothesis presentation for Flat Earth. And this was inspired by a presentation that was done by Mike Heffron about 2 weeks back now. And during that, he presented an argumentation of arguing from the null hypothesis and trying to falsify your null hypothesis and provide evidence against it. You know, if you can reject it for an alternative hypothesis, you know, that would be ideal. So the way that I have this laid out, I'm going to have a null and an alternative hypothesis, and we're going to go over evidence that is mutually exclusive or that provides a mutually exclusive outcome based on the parameters. And after we tally those up, we'll see how many of those are in favor of the null or are in favor of the alternative hypothesis if we can falsify the null. Okay, so this is going to be answering the age-old question, especially in regards to you know, recent events regarding the final experiment with the 24-hour sun. You know, is Flat Earth dead? Did that kill it? So this is in regards to that, proving the shape of the Earth with things in the sky. I would argue that you can't do that, but what you can do is use the objects in the sky to show you what the shape of the Earth isn't. And I think that's a much stronger position to take. And as we go through the argumentation, I think, you know, you guys will see why. So the null hypothesis, to kind of break this down, to add, because this is going to be some new terminology for everyone. A null hypothesis is the thing that you're assuming to be true, and then you'll find evidence against it so that you can reject it. And you'll have a competing alternative hypothesis, typically, that goes in tandem with your null, and those will be mutually exclusive in terms of their explanatory power for whatever your hypothesis is. So you can't, in other words, they're not going to be the same outcome. They have to be different. So your null and your alternative have to be different. So this is similar logic to you can't prove a negative. So if you say that unicorns are real and I say they're not real, you have to show me evidence that they're real because I can't prove that they're not real, right? That's you can't prove a negative. So it's like following that same kind of logic. So in this example, though, for the null hypothesis, let's run it with the same scenario. So the null hypothesis would be that unicorns don't exist, and the alternative would be that unicorns do exist. Now we have our mutually exclusive claims, and they can't both be true. So if you were to start providing evidence of the existence of unicorns, you would have to provide at least 4 unicorns, right? Because the first one could be a genetic mutation, the other 2 could be, you know, some weird anomaly or whatever. You'd have to provide 4 for statistical significance to falsify the null hypothesis in favor of the competing hypothesis that they do exist. So hopefully that makes sense in how this is going to work out. So now that we've got our, go ahead.
Is this open? Can I just jump in right now, or are you doing a thing here?
Doing a thing, but if you have a question or a comment, feel free.
Just for the last thing you said, if I say there's no black swans, you'd have to come up with 4 black swans, you said, and not one, just to make sure it's not like painted black or something.
Yeah,
like
yeah.
a bunch of them, so we get like a.
Yep. So yeah, this is in regards to
repeatability.
Statistical significance out of it. Yeah. So when if you've ever heard of, like I have sigma 4 confidence, I have sigma 5 confidence. This is out of a statistical analysis of the data in regards to how that data supports like a null hypothesis. So like, because I'm sure you've heard, like, you can't prove anything in science, but you can provide evidence for it. Right. So this is in the same regard. So it would be like to provide statistical significance to say that your confidence in this being the truth is, 99%. You would have to have, a data set that you would be able to extrapolate that from.
Yeah, the word I was thinking, like robust, like if it's robust enough to be able to have enough backing to it in order to actually falsify. Is that like, is it quantitative in that way?
Yes.
Qualitative and quantitative.
Yep. So for our null here, for our null hypothesis, we have the Earth is planar, and measurements of curvature are dependent on the position of celestial bodies. So this logically follows that the Earth is planar, and that any curvature perceived will be optical. And then we have the competing hypothesis, RH1, is going to be the Earth is globular, and measurements of curvature are independent of the position of celestial bodies. So this logically follows that the Earth is physically shaped as a globe, and that the curvature is physical. Now we have a little video here on maps, but I'm not gonna play it because I don't want to lose momentum. Because like I said, this is a long Prezi, but I will give you guys the link. You can check it out in your own time. But basically, the TLDR of this video is that maps can be used to project a whole bunch of different things, and they don't necessarily represent what they're showing you. And here we have a sample size of a ton. Well, they give the example here. Back in the day, everyone was super into the Mercator map. And then when World War I was happening, more flights were going overseas. And then they found that they couldn't use that map because it was showing positions of locations in the wrong spot. So there was this whole big thing. But anyway, it's a cool video. Check it out. They go over the history of that and how they changed maps and all the propaganda that went on with that, and what you can do with maps to give importance to certain regions during certain political times to make it seem like, oh, this is like a threat. These people are right here, but it's just a projection that makes that area of the latitudes look larger, etc. So anyway, we have all these different projections that a coordinate system can be projected on, because that's the beauty of these maps, right? What do all these maps have in common? They all share the same coordinate system, and this is called the graticule. And this is represented by the latitude and longitude lines. That coordinate system can be used to be projected onto all these different types of maps, and they'll all represent the same thing. So you can represent distances and routes all the same. You just have to apply the correct transformation, and everything will transform invariantly. So that's the beauty of the coordinate system. And because they can be projected into so many different projections and shape types, how do we know if the coordinate system truly represents the shape of the Earth, meaning that it represents an Earth that has physical Earth curvature, or if it represents an Earth that's, say, flat and has two star fields, one in the north, one in the south, and and everything is mapped to your radius of vision. How could we tell the difference, right? Because if you merge two hemispheres together, mathematically, that would complete a globe, and you would have a spherical coordinate system that could then be projected into all these. But the baseline measurements of it would be based on two planar hemispheres, right? Where the stars go above you and complete a circuit, whereas on the globe, they would go beneath your feet to complete the circuit. But mathematically, those would be represented by the same thing. It just, when they go out of your vision or go beneath your feet, they would be on the negative side of the coordinate system. There would be no distinction mathematically. And you could merge those two observations by taking two hemispheres, right? You just make a ball out of it, right? And then you would have the completion of the spherical coordinate system represented by what you can see based on your latitude and time. All right, so how do we know which one's correct, though? Is basically the point I'm getting at, because there's a lot of those. The azimuthal, cylindrical, conical, all these different projections, all saying the same thing, but all coming from a spherical coordinate system. So we have to determine how this... we have to determine if we can, what this coordinate system represents in reality. Does it represent Earth curve, or does it represent something else? So as we get into that, we're going to look at curved visual space versus Euclidean. Now, the way that the map was built, right, was based off of measurements through optics. So using theodolites, using positions of stars. So perspective is going to be highly relevant for determining the information that the map was built upon. So we're going to take a look at that. So this is going to be optical curvature versus physical Earth curvature. So we have some examples here, some real basic ones. Now we have railroad tracks converging at a distance. Now in Euclidean geometry, in the spatial field, right, where things exist in 3D reality and are mapped, these train tracks never converge, right? They obviously go on parallel in perpetuity until they reach their destination, right? But optically, they converge. So there's a divergence from the spatial field and the visual field, represented by your optics. The visual field is how you perceive things, right? So there's two different fields, the spatial field and the visual field. And we see the divergence here from the two, because in reality, we know that these train tracks never converge, but optically, they converge. And we have some various examples here of shadows being cast by a mountain. And some will say that this is due to Earth curvature. And as you're rotating away from the sun, the sun, being underneath the mountain at that point is casting a shadow upward. But on the right-hand side here, when you go on top of the mountain, you'll see that it's cast down. So it's just a perspective thing. This isn't a geometric proof of a globe, because if it were, you wouldn't have the shadow from above representing the same thing. It would only be the one-sided version of it. But in this case, the sun is always above the horizon, and it casts a shadow based on, and you see, and the way that you see it is based on where you're looking at it from. So we get this divergent and convergent effect where the spatial field and visual fields, don't seem to overlap there. So we'll get into a little bit of what that means and how, optics works explicitly, and how star maps were made, because the star maps are going to be relevant for making a ground map. Because it turns out that the maps are based off of all positions of the stars on a specific day. So the dome of vision, sometimes we'll call it, or the azimuthal grid. We have different slang terms and whatnot for it. But what happened was in the 1800s, when the Royal Society was doing observations, they had a telescope mounted such that it was looking horizontally, and then they could tilt it upwards 180 degrees to the other side and look at the horizon opposite. So they basically would map this out as a dome because that's how you perceive it. And when you look at stellarium and you see that dome of vision like that, how it's all mapped, that's all derived optically. That's exactly how you perceive it. You perceive it in a dome, and we'll go over some examples of that because what's put forward is that to make this star map and to make this model work that's associated with the map is that starlight has to all come in parallel, and the contour of the Earth, meaning the curvature of it, is going to dictate how you see that incoming parallel light, and that's going to cause positions of the objects in the sky to move. So we're going to examine, is this an optical effect or is this due to Earth curvature? That's the purpose of this, of going back through the history of this and understanding how our perception of the sky, where it came from and how it's used today. Because as we're going to find out, the positions of the stars are always in the, they return back to the same spot hundreds of years later to make this map and coordinate system useful. So understanding how we perceive it is going to be extremely important moving forward. So this is from Dr. Carl Lundberg in the 1940s, where he's writing about his hypothesis on curved visual space. And his hypothesis was that curved visual space is hyperbolic and that the curvature rate is constant. Now, it turns out that the curvature rate is not constant, but this was back in the 40s. Anyway, he put forward an interesting argument for curved visual space here that I'm going to now lay out. So he says that astronomical objects like the sun or the moon are seen at finite distances, and they are sensed in a way that is not proportional to their astronomical dimensions. So in other words, if this parallel light ray story were true and visual space was also Euclidean and came in with parallel, with that parallel perception of the rays, we would see the sun as it would take up the entire sky. The sun is 860,000 kilometers wide, and we're in the center of it, based on our orbit, assumed orbit. And based off of those dimensions, if the light rays come in parallel, then the sun is all we would see in the sky. It would be the biggest thing ever. Right. And even more, the stars are said to be, which are said to be suns, but they're like, what are they? They're, hundreds and thousands of times larger than the 860,000 kilometer sun, but we only see them as tiny dots. So in order for this to work, there has to be some convergence of the light rays to make everything into a focal point. It can't be that we see in Euclidean space. And that was an argument that he made to intro into the subject. And if you think about it, I mean, we see the sun and the moon as the same size at what is like half a degree in angular resolution, angular size. And in order for that to be the case, based on their actual, given distances, assuming the correctness of the model and the correctness of Euclidean visual field, then they should be the biggest things in the sky. So we have a clip here from a book from 1892. Actually, it's not from 1892. That citation's wrong. I'll have to get the exact date, but it's a little earlier than that. I think it's 1920s. But anyway, what he says here is overhead is the dome of heaven. So he's describing here how you perceive the celestial bodies in the sky. So like if you take that stellarium, imagine a picture of stellarium right here next to that would be what you're looking up and seeing. This would be the God's eye orthogonal view if you could look at somebody and how they're perceiving the sky. So this is the description given. Overhead is the dome of the heavens, which so far which so far as it has been determined by the actual positions of the visual bodies like the heavenly orbs, or by the values of the sky, or by the clouds, has in no reality, no definable shape, but may be geometrically regarded as a hemisphere with a center. So you have your own little hemisphere of vision there. Okay. This is not indeed the natural idea of the observer, whom the dome of the heavens appears to have somewhat a flattened form, the horizon being between 3 times as far away as the region overhead. Considering a cloudy sky, we have to remember, if we are to rightly understand what we see, that usually the curved surface at which we look up is flatter even than this. We mistakenly attribute it to the dome shape of the heavens, whereas in reality, the curvature is no greater than the curvature of Earth itself, which under ordinary conditions is imperceptible. So here we're going to get into the coordinate system, how we perceive things, and ground curvature versus optical curvature. Because he's saying here that there's an equivalence between how far you can see in this celestial dome of vision versus Earth curvature, and they're identical. And if you guys have caught any of Shane's presentations or are familiar with Shane's database, the 69 mile per degree page in particular, where everything is derived from your optical limits and radius of vision, that's equivalent to 3959. So basically, when we get into the use of this coordinate system, what we're going to find out is that even though they tell us the sun is 93 million miles away, Saturn is 600 million miles away, different various stars are light years away, hundreds of millions, thousands of light years away, etc., between these various stars, none of that actually matters. And for use of the coordinate system for celestial navigation to tell where you're at on this Earth, you can assume that everything is at an equidistant web at the limit of your vision. And that distance is what is used for terrestrial meridians. So the distance from the North Pole to the equator, that limit of vision, if you were to flatten that out and take, 19 times 90, you would get 6,218. So that would be the distance for that. So that you would just take your degrees and latitudes in between from the equator to the North Pole, and that would give you the linear distance. Like if you were to take your dome of vision and flatten it out, essentially, that's what that distance would represent in that coordinate system. So the optical equivalence here, what we're looking at so far is that we have a perceived dome of vision, and we have the asserted. We also have the asserted Earth curvature, and that the visual perception of it is just an illusion due to Earth curvature, which is identical to optical curvature. Okay. All right. So we're going to learn a little bit about the history of spherical excess and curvature on a sphere, or curvature on a curved surface. So this is from Direct Measurement of Curved Visual Space, 2002. The notion of intrinsic curvature was introduced by Gauss in a seminal paper dating back to 1837. Although the theory is arcane to psychophysicists, some of its consequences are relatively easy to grasp. Intrinsic curvature differs from extrinsic curvature. A flat piece of paper remains intrinsically flat when you roll it into a cylinder or a cone, although its extrinsic curvature may change. Intrinsic curvature is evident from certain non-Euclidean properties of figures. One example treated by Gauss concerns the sum of interior angles of a triangle made up of geodesics, the shortest arcs or straight lines. In Euclidean plane, the sum is 180 degrees. Any deviation is called angular excess, which reveals the intrinsic curvature of space. The excess is proportional to the area of the triangle. The excess per unit area is a measurement of the intrinsic curvature. Notice that this physical dimension is 1 over the square, thus the inverse of the square root of the specific angular excess has the dimension of length. Gauss showed that it simply equals the radius in the case of a spherical surface. So you can take the angular excess over the area of a triangle and deduce what the radius of the triangle and deduce what the radius of the sphere is that you measured that produced that angular excess. So there's a relationship there that he established. So in other words, if you have a defined radius and you can figure out what the spherical excess would be over the area of any given triangle on the surface of that, and vice versa. So to give an example here for areas of spherical excess, now if you take an equilateral triangle of 1 kilometer over the surface of the Earth, you'll have a spherical excess of 0.002 arc seconds, which is imperceptible. You never know. That's what they were saying there. It's imperceptible, right? But over a large distance, this is where you would get, noticeable curvature. So if you take the distance from Boston, somewhere in England, and Cape Town, what you'll get is a spherical excess of 0.0057 or 507. And that, using Gauss's theorem there, you can get back to a radius of 3959 using that. Yo, what's up, Jeremy?
No, I said your name wrong. I just wanted to ask you a couple questions after this that
okay.
entails this whole thing. But go ahead, carry on, please.
Okay, no worries. Okay. Yeah. So over large distances, the calculative value will get you back to the radius. Okay. So we have this radius of vision, this perceived way to see the heavens. We have curved visual space, which is a divergence from the spatial field, which they say is Euclidean. And in regards to positions of celestial bodies, take the sun, for example, we have everything and how we perceive it being mapped to this dome. So we have a manual here from the 60s on solar panels and how the motion of the sun across the sky throughout the day works relative to the time of year, and how you need to position your solar panels based on how this works. So what they're saying here is, like, there's this physical sun that you would be seeing, and then this is what you would actually see. Like, you would see this apparent position right here. See this curved map he's holding. This is where he's perceiving the sun versus its quote unquote true position. So no one actually sees any true position of the sun or the moon or any of the stars or anything like that. They're all apparent positions, which we'll get into as we continue. But this is laying out that everyone has a dome of vision that they perceive the heavens in, and this is how you map that to in relation to ground elevation angles to the ground with respect to where the sun is. Now we have the moon here being commented on by NASA and its apparent position and how you see in a dome, and as it's going to arc across the sky. So this is even them laying this out, and this was taken off their website, but this is just reiterating the same thing. And actually the YouTube channel Vsauce has a really nice video on curved visual space. If you go to his channel, go to Vsauce on YouTube and search for moon terminator illusion. That's a really nice video on curved visual space. He covers it quite well and how different things will affect your perception. Now, in addition to that, we have sunbeams that go to your feet, and then somebody standing, 10, 20 feet next to you, they won't see the beam that's going to your feet. They'll have their own personalized beam. So this is just in regards to everyone having their own dome of vision of how they perceive the sky. We don't see the true positions of anything. Everything is personal to us, but represents positions over the ground, or approximate positions over the ground. Should be better stated, but we'll get into that. And anyway, moonbeams have the same effect. I just haven't added the screenshots for it, but you can Google it. Just Google sunbeams at the beach and moonbeam at the beach. Same situation. So these are all personalized phenomenon to us from the sky that occur in our dome of vision. Okay, so to recap here, we have a dome of vision, and we also have the assertion of physical Earth curve. So now we're going to get into measurements to try and determine which of these hypotheses is true. So starting off with measurements of the ground, we have astrogeodetic surveying, which if you guys have ever heard the argument, you can get, if you're looking for spherical excess, go to mctune.net/se and download the Arc of the Parallel, and you can learn all about how the lads got together and measured spherical excess. Well, how did they do that? What does that mean exactly? Did they get a bunch of rulers out and start measuring the ground and come up with 8 inches per mile squared? Like, what happened there? How was all this determined? So we're going to examine the process for astrogeodetic surveying, otherwise known as geodetic surveying, but it is all in reference to the stars, as we'll see here. And when we get into the two competing models that had to be overlaid, one is the ellipsoid model. They tell us that the Earth's an oblate spheroid, and they also tell us that that there's a gravitational potential model that needs corrections for too, otherwise known as the GSW 84. I'm sure we're all familiar with that. We've all heard of that.
What are you doing about, man?
What? Is that SE? Anyway.
Hey guys, if you're unaware, Alan is doing a presentation right now.
Yeah, if you do have questions, feel free to ask them between slides. But yeah, otherwise, just trying to get through this here. So let's see. Positions of the stars are going to dictate. Let's see, where were we at? Kind of lost my train of thought here. Oh, anyway, positions of the stars are going to be heavily referenced in these ground measurements because the deviations from the expected positions is going to be where they're going to reference curvature and for those deviations. So this is in reference to the usefulness of the coordinate system and how it works. So to use this, the exact dimensions of to make this coordinates, the graticule effectively, or to make the graticule effective, to make that spherical coordinate system that works on all these different map projections, to make it useful, you have to have exact dimensions of the Earth so that you can computate distances, because what they're going to do is, or what the working assumption was, is that you could take a cosine to a star and use the relationship with the altitude and the angle to determine a distance. And then what they would do is they would calculate that out, and then they would travel underneath that star until it was at their zenith, right at their 90 degrees. And then they would look up with a telescope or theodolite or what have you. And it was expected that if they leveled out that instrument, that when they looked up with that telescope, the star would be in the exact center of that eyepiece, because they're making a triangle following cosines. For 90 degrees, they're not using hyperbolic trigonometric functions or anything like that. So they would expect to be right underneath that star, and when they look up, based off of having the device leveled, they should have that star right in the center of that piece. And no matter how hard they try, they could never get it in the center. So all of this is based off of the Nautical Almanac. So when you get into geodetic surveying and the comparison between the stars and whatnot, they're going to heavily reference the true positions of the stars based on the Nautical Almanac. And that is basically if you were to look up at the sky on the vernal equinox, so in the spring equinox, if you were to look up at the sky and take a snapshot of the position of all the stars, and you were to, basically make triangles to all these stars based off of their elevation angle where you perceive them at, and then go underneath them and look up to confirm that that's exactly where that star is at. That's what this is all based off of. And what they found when they started doing that was that the stars were never directly in the center of their telescope. They were always off a little bit, and they had to correct it a little bit. And they started calling these corrections, these deviations from a perfect celestial sphere, they said that they were due to the oblateness of Earth, meaning that the Earth is slightly flat or slightly curved in certain areas. And due to that, they have to, physically the equivalent would be to physically tilt their device to put it in the center. And so they're saying, how much do we have to tilt our telescope or our theodolite to get the star to be in the center where it should be from its expected position? It's, you know, it's quote unquote true position. And they take that difference, and that's where they're getting Earth curvature. When they add all these up over different locations, those deviations then become Earth curvature. So this is where spherical excess comes from. So that relationship earlier that I talked about, where if you know the radius, you can get back to the, or you could derive the angular excess and vice versa. So when they have a model for a celestial sphere of a radius of 3959, and they're using that ellipsoid model of the same radius, and they have deviations from the two, this is how the difference is how they got the reference ellipsoid. That's how they got the shape based off of those deviations. So again, this is just reiterating that exact position about how everything is derived from the correct position of the stars, and you need to account for certain effects to get everything in the true position versus where you actually see it, because there's various reasons given as to why you don't see it in its actual position. One of which is gravitational. Earth curvature. You know, due to the oblateness or gravitational potential corrections, which we'll get into as we continue. But before we do that, we've been referencing the stars a lot and the true positions of them, and how this coordinate system is in reference to a snapshot of these idealized calculated true positions using mathematical laws versus physical ground measurements, right? So what I was putting forward earlier, that everything that we see in the sky is, you know, it's like personal to us, and it's in our dome of vision. It's not based off of physical objects. What was done in the 1800s, there was a hypothesis from a guy named Arago, and it was that if the Earth was moving, he would have to adjust the focal length of his telescope every 6 months, because the Earth would be moving towards or away from the starlight. And what he found was that he didn't have to adjust it at all. So even though the sky is moving, right, like you can look at it like kinematically, either the sky is moving and we're stationary, or the Earth's moving and the sky is stationary. Either way you look at it, if the fact that he didn't have to adjust the focal length on his telescope shows that there's no relative distance change between the two throughout the year, despite the fact that in both geocentric and heliocentric models, there would be a distance change, but there's no perceived change in that regard. So there was no adjustment required, which I think further adds to my argument that what we perceive is personalized to us, and it's always apparent positions of objects. They don't represent physical objects. In a follow-up experiment done by Arago, he was using a crystal prism to half cover a telescope to see if the starlight that was incoming to the telescope would have to require a correction, like an angle change, because of Earth's motion underneath it. So the idea was he was going to slow the light down in this part of the medium here, where it was half covered, and when the starlight was in the center, if the Earth is in motion, he would have to tilt this further. And what he found was that he didn't have to tilt it at all. Or in other words, no further correction was needed, which implies that the light is already coming in at that angle and the Earth is stationary. So what can be said is that light comes in with a horizontal drift to it, and if the reason that these people, when they do their cosines and go underneath a star and look up, the reason that they can never get the star in the center is because everything that they see is an apparent, it's in an apparent location, and it already comes in at that angle. So the idea that there's this idealized location and there's deviations from that is, you know, kind of a role play, because this is just how it is. You can't make a perfect triangle out of this. And then this was also further backed up by Airy, who did his measurements with a zenith mounted telescope that he could rotate 180 degrees around a spindle using a micrometer, which is micrometer thickness wire, and he used a grid formation to put the star in that with the zenith mount, and then he was measuring the deviations from where it was expected to be in this grid, and each wire thickness would represent 1 arc second. So he could you could basically translate a distance on the celestial sphere to the ground. Like, that's how they're linking the two measurements, because all units of measurement, as it turns out, are ratios of a terrestrial meridian of the graticule of the coordinate system that's in use. That's why you can take a cosine to a star and then go a distance using a unit of measurement derived from the coordinate system itself. That's why that works. So in relating these two, the celestial sphere and what was it, a millimeter, you can determine distances. And so this is what he was doing with that. And what he found when Airy introduced water to his telescope was that no additional correction angle was necessary. So just kind of further illustrating that the light already comes in that way, and these idealized positions of true positions don't mean anything. But however, right, I'll say this, they are necessary for a reference for the accuracy of the coordinate system. Like how it was stated earlier, the exact dimensions, et cetera, must be known, right? So we get fed this story about Eratosthenes, who used a shadow to derive a pretty close radius to the exact radius, and his units of measurement, the stadia, would just happen to be a ratio of a terrestrial meridian that agrees up to 99.9% of the current values. It's like, oh, okay, cool. But we have all these stories that give to the exactness of the coordinate system that's used. So you think that these are the dimensions of what you live on, but that's not necessarily true. But the accuracy of, like, the use and accuracy of it is dependent on, like, these idealized conditions for reference, so that you can accurately use the system. Because what it's going to come down to is timing. Oh no, the GIF doesn't play. That sucks. What it's going to come down to after they've established the zenith positions of the stars, where they've taken the ground measurements to establish a position, or, you know, a GP with every star to correlate to a position on the ground. After they've done that, they need to look at transits over the meridian lines to make everything line up with that, and that's going to require them to get into timing. So that's where they get into, like, the pendulum clock and little watches and all that, with the story with Newton. So, like, this is all, and then the those timing differences are all in reference to that idealized time provided by that snapshot on the equinox. So this is what makes the accuracy of the system. It doesn't have anything to do with the shape of the Earth so far. So far, we just have lads calculating things and, you know, taking timing differences and differences in measurements and then making some assumptions. But so far, no one's measured the Earth yet. And then we have in this GIF here, which you can't see, but basically it goes over nautical miles and how everything is a ratio of that, including the stadia, which is a ratio of a terrestrial meridian that agrees up to 99.99997%, agreed upon by scholars, which you can just reverse engineer based off of the, because there's no, like, defined, what was it? There's no, like, agreed upon, like, oh, the stadia was this exact amount. Like, nobody knows, right? But you can reverse engineer what the stadia would be based off of the radius of the Earth and the angle given that they're attributing to the radius of the Earth. So you can, like, you can basically just algebraically solve for X, and then that'll be the stadia. And that's, like, what they did. So when they talk about how he made this approximation that was close to Earth's radius, Eratosthenes. That's what they're. That's how that was able to happen, right? It's not like a stadia was an independent unit of measurement that just happened to be the same as Earth radius. Scholars agreed upon making it a ratio of what all units of measurement, are today, which is little fractions of the terrestrial meridian, which is the length of a latitude line from the North Pole to the equator. Okay, so to recap from ARI here, we have starlight comes in at the same angle, so that doesn't require any additional corrections. So it's always apparent is the TLDR takeaway from that. And Man of Stone just put together an awesome video on ARI's failure as well. And as it turns out, the difference here was for the first 6 months. And when you add the other 6 months, it's actually just a null measurement. It doesn't, because they overlap, there's actually no difference. So it's just kind of reiterating the starlight comes in at that angle. So definitely head over to bitshoot.com. Check out Man of Stone's video that he just put out on this. It was really good. So here's what the star constellations and positions of the stars would look like over an azimuthal projection. So we just took the normal projection that you would see and just put it over an AE map so you can see what that would look like. So imagine a bunch of dudes getting together and walking around and taking zenith measurements of stars instead of seeing all the continents and stuff. Well, all of that was dictated and measured and in reference to positions of the stars. So another way to conceptualize any map is a position of where the stars are at a specific time. All right. Any questions so far? I'm going to get some water real quick.
Yeah, you're doing great. It's all good. Go ahead and do that. Anybody have questions though? In the meantime.
All right, cool. Cool. Got some water. All right, so for astrogeodetic surveying, where they went around and took these measurements, like I was saying earlier, the first ellipsoid measurements that supplemented the nautical almanac, which is said to contain the true positions of the stars. And how did we get these measurements? Well, it was in the 60s, the Crown put out a document called the Supplement Explanatory Corrections for the Nautical Almanac, the American Ephemeris, and all these other different ephemerises, a couple other ones. And basically the TLDR of that book is we went around, took zenith position measurements of these stars from where we expected them to be, and there were deviations, and that's where we got our ellipsoid. And everyone's like, oh, okay, cool. And then now we have the arc of the parallel measurements where they were using the confirmed reference ellipsoid that that the documentation was provided from the Crown. And so now we're going to look at the overlap here between this new geoidal potential model here, which is going to be the gravitational potential corrections, where during the surveying they went around for the arc of the parallel, and as they did this, what they found was the measurements were sub 180 degrees, and to get them to be over 180 degrees, these measurements have to be in reference to something. Because here's the thing, right? We have people that say the Earth is measured flat. We have people that say the Earth is measured curve. Well, they can't be measured flat and curved. Who's right? Is it Johnny Theodolite, or is it or is it the geodetic surveying people, right? Who's right? How do we know? So we have to use an external reference, it turns out, and it's going to be the stars, because Earth curvature, as measured from these, all shows that there's all measurements horizontally, right, end up being sub 180 degrees. And to get the exact positions and more accuracy to it, they have to reference the stars. That's what's going to constantly be referenced when you go over the arc of the parallel, is corrections and astronomical corrections. And what they're doing is they're making triangles in the sky, essentially, right? They're idealized triangles, and then they're transforming them on the ground, and any deviation, optical or physical, due to Earth curve, like the difference in those two is how they're comparing it. So as it turns out, there's going to be no independent measurements of Earth curvature. It's always going to be in reference to celestial bodies. So this is what we're going to get into here with the deflection of the vertical. So the first correction for the deflection of the vertical was due to, the Earth's oblateness, right? The shape, the offset. Now this next one is going to be due to gravitational potential offset. So what they're going to say is halfway through the arc of the parallel survey, they didn't have enough measurements that were over 180 degrees. So what they did was they said, oh, you know what? At this location, when I drop my plug bob, it's not going to the center of the ball due to gravity like we would expect it to. So my theodolite isn't actually level. And to get it to, but I know where level's at. Level, if this telescope were truly level, right, then this star would be in this exact position in my theodolite. So all I need to do to find out where true level is take the difference from where the star is measured at and where it's expected to be at. And that offset will be, I'll call that deflection of the vertical. I'll call that a correction for the gravitational potential, because you have to be perpendicular to the gravitational potential, right? So if you think about, a circle, and you have to maintain like a perpendicular relationship with that, with that circle. So you're always going to be tilted a little bit. And that's basically what they're asserting here. And we'll look at a nice diagram for what that looks like, right? So the gravity vector, they're saying in this specific area, is pulling the plug bob in a different direction. So we have to tilt it back to get the perfect level. So our perfect level reference is going to be where this star is supposed to be, and the difference in the actual measurement due to the gravitational vector. So this is how they're establishing these measurements of curvature based on these deviations. And these are just calculative values to explain why this star isn't in the exact position when it was already experimentally established in the 1800s. That starlight comes in at an angle, and the idea that that there's like an idealized physical location, a true position for these, is just, not a realistic thing. All right, so these are some excerpts from some various surveying papers and manuals that are talking about, 20 arc second corrections, and then some in Australia that are up to 30 arc seconds. So basically, let me show you the units of measurement real quick. So if you take the distance between 1 and 2 degrees and break that into 60 sections, you would have 60 arc minutes. And then if you break each arc minute into another 60 sections for 60 seconds for 1 minute, or for 60 seconds per 1 minute, you would have an even smaller ratio there. So you would be able to break a degree down to 1/3600th of a degree for an arc second. So that's what we're dealing with these measurements for these angles. So they're saying that that these stars and whatnot are out of place by 20 of these little baby arc seconds. So that's what that's the scale we're working with there. And then when they get into surveying specifically for the arc of the parallel and whatnot, we have a bunch of refraction coefficients that can be used and swapped out based on what geographic location you're in. And all of these are basically extending Earth's radius to make any measurement comport to the globe. So if you were to extend the Earth's radius, you're basically making it bigger and flatter, because you know how the Earth is so big, you would say, Well, it's just locally flat because that's what we can perceive because, we're so tiny on this big Earth. So if you start to see things that go past a certain geometric limit, you could say, okay, well, what's happening is there's refraction, and what the equivalent of that is doing is saying like the Earth is actually just much bigger, and therefore like the areas of flatness are just longer. So throughout the day, you'll have different refractive indexes that'll change, and you'll use different coefficients to adjust for the radius at that time. So basically, turning all. Can you please mute your hot mic and while clearing your throat? Thank you. So what you're doing is you're just turning any optical measurement into a planar measurement. So that would be like yielding physical curvature and then making it as a function of optics. So that's an equivalence there between the two. So again, we're not getting anywhere without referencing an external system, which would be the stars in this scenario. So nobody's out there measuring curvature, and they're actually taking measurements and then turning them into planar equivalents using different refractive indexes. And I even seen recently from and we're not going to get into that, but that was really funny. Basically, somebody was saying that you can see forever based off of the refractive conditions, and it was just like, well, thanks for being honest about it, I guess. But anyway, all of these are just basically reaffirming the same thing. Now that they've got the reference ellipsoid model for the first deviations, we're now taking finer measurements and doing the same thing, and then calling the corrections using the same corrections but attributing them to a different cause now. So now it's a gravitational potential. So when you look at the what they showed in this diagram, let's see. Yep, it's coming up. 1 second. What they show you here is this ellipsoid, right? That would be like the oblateness of Earth. And then they have this geoid. Well, what's a geoid? There's no such thing as a geoid. This isn't like a physical, this isn't like a rock shape, right? This outline for the geoid is the gravitational potential differences that you have to maintain your perpendicular relationship to. So these are what are facilitating this correction right here. So the ellipsoid and the geoid intersect, but they're hypothetical models, right? That all have a baseline of a perfect sphere, which is the celestial sphere. So again, to give a visual of what's happening here, we have horizontal measurements on the ground that are coming out to sub 180 degrees, being in favor of a plane. And then we have a reference in the sky using cosines to give us a triangle to have like a perfect deviation from. Then we're comparing the two, and we're calling the difference spherical excess. We're calling any corrections needed. We're going to attribute that to spherical excess. And because we have an exact radius for the usefulness of the map for the dimensions and everything, anything that doesn't comport with measurements that after corrections are going to yield the spherical excess needed to get back to the radius that we need, we're just not even going to write those down. We'll just throw them out, and we'll get into that. So this is from the glossary of the arc of the parallel, getting into the corrections of the observed latitude and azimuthal longitudes and variations of pole rotations and all this. And basically, if you open this book and Control F it and type corrections in it, you'll cycle through all the early references of how they're correct, like where all these astronomical corrections are coming from. So this is just basically, it's almost a book of not only, surveying, but of astronomical measurements as well, because this is what the whole book is in reference to. So just going through, I'm just going to scroll through some of this here. This is all just reiterating the same thing. Basically, the measurements come from the difference in the sky and yada, yada. And when there's a discrepancy, if the measurements don't comport, they just throw them out.
So here we have some calculated values here, all adding up to sub 180 degrees. But, after a couple of corrections and whatnot, a couple of them do end up coming out to 180 plus arc seconds, or 180 degrees, to the tune of 180.0. It's like just an insanely small deviation that can't really be quantified without referencing the stars. So there's nothing really there. And then in 1776, by royal decree, it was stated that everyone had to use the latitude longitude coordinate system. Otherwise, you were going to be fined 30 shillings. And this coordinate system it's the coordinate system that we're all using to this day. So that coordinate system that goes on all these different projections and all this was royally decreed to us in the 1700s. Okay. And then in addition to that, there was a bounty that was put out in this decree where the king was saying, hey, there's also some problems with the coordinate system that we're trying to refine. And we're hiring astronomers and mathematicians to go out on an expedition where 2 ships are going to circumnavigate Great Britain opposite to one another using the stars and this coordinate system. And whatever corrections you have to use to make this 2-party system work, we'll reward you with 10,500 gold shekels. So that was very cool of them. And it seems like they got that all worked out because celestial navigation and this coordinate system that we all use today seems to be working. So it was nice of them to get that sorted out. But that was what was put forward in the 1700s for this. So they've been at this for a long time, because we've often heard, where's your map, flat earther, and all this stuff. And it's like, bro, they've been at this for like 400 years with unlimited funding. So anyway, this is just a clip from the supplemental, or the explanatory supplement to the Astronomical Ephemeris and the American Ephemeris and Nautical Almanac. Basically the measurements that came up with the reference ellipsoid, showing how that was done. So they got the fundamental plane. So each, your hemisphere of vision dictates the position of the stars. Everything under you would be where you don't see, at the limit of your vision. They're assuming things go under you at that point, whereas our position would be that that's just out of your dome of vision. And as you move forward, you would see it. Anyway, so yeah, no direct summary there, no direct measurements of Earth curvature, always in reference to the position of the stars. If you have a theodolite and you're making no assumptions, and you're just like, hey, I'm just looking at this mountain, I'm just looking at this object XYZ, I'm just looking at this thing, and it seems to be below my theodolite crosshair, seems to be below the horizon, seems to be due to Earth curvature, seems, what kind of possible mechanisms could we introduce? Well, we've established that the measurements alone can't tell us anything, because optically it could be an optical phenomenon, or it could be a physical Earth curvature phenomenon, or it could be a combination of the two, where you have refraction, you introduce refraction into the Earth curvature to make it, which turns the measurements into the planar equivalent. Could be any one of these things, but needless to say, it's only been substantiated in reference to the stars so far. So what can we do to, what else can we do to get some geometrically defining outcomes that are going to give us a different outcome, right? Because looking at apparent positions of stars and referencing a coordinate system, and then doing horizontal measurements and comparing the difference could go either way, right? Could go either way. So a geometrically defining property of sunsets on a globe is that the sun is going below the horizon due to the Earth rotating out from underneath it, which is going to produce certain effects at sunset when the light is vanishing, right? Certain things are going to have to occur. So we have a model here provided by, I think it was Shadow Sovereign, whose video was put on Taboo Conspiracies channel. So this is a little clip from it real quick. 1 second. I'm going to grab some water. All right. So let's see. We have the picture here. So we have two predictions for the geometry of shadows based on the contour of the Earth. So on a plane, what would happen is these pillars here casting a shadow, the shadow being cast by them will never exceed the height of the pillars themselves. And this window in the back that's casting a shadow will never be higher than the window that's casting it. And at a certain point, what'll happen is as the sun gets further away and this shadow starts to climb up this wall, there will be a certain point where the shadow starts to slow down, and then it'll eventually remain stationary, and then it'll fade out. So that's the prediction for the Earth being a plane and the sun always being above the horizon. And the prediction for a globe is that the sun is going to be setting because of it going around the curvature. So what's going to happen due to that sun being physically lower in the horizon, what's going to happen to these shadows is these pillars are going to cast shadows that are going to exceed the height of the pillars themselves. This window is casting a shadow that's going to climb up this wall and exceed the height of the window. And as that happens, there's also going to be an abrupt end as a uniform shadow streaks across the land due to Earth curvature and the ball rotating at 15 degrees per hour. So these are going to be two different outcomes that are geometrically defining, right? So one predicts that the sun is always above us. The other predicts that the sun is going below us. And keep in mind, this model is not to scale. This is just to show us what would happen. We'll take a look at a real world observation here in a second so we can see what happens in reality. But this is just to show you the difference. So at sunset, what would happen is these pillars, their shadow would be cast super high. We already have the abrupt shadow incoming to end everything from Earth curvature as the ball rotates away from the sun. So this is going to be like our hard end that's coming up over all the other shadows, and it already overtook the pillars. And here we can see that the window before the shadow overtook everything was being casted above the window that's casting it, and then now we can see that the big shadow is climbing up the wall as well to put an end to it. And now on a flat Earth, where the sun is above the horizon at all times, what we see is that the shadows climb up the wall, but they do not exceed the height of the pillars. And same with the window, it starts to climb up, never exceeds the height of the window, and then it fades out. So we have some examples here from Man of Stone, whose house is facing west. At sunset, the exact scenario that we just looked at a model plays out. So the shadow begins to rise a little bit. Then it remains stationary at this point where it starts to fade out. So you can see the fading here. We don't have an abrupt end. There's none of that. And to give you guys a video of that, you can watch the model, and Man of Stone's video was spliced in at the end so you can see what happens. But I put a link in the thing there so you guys can see it. But that's a mutually exclusive outcome there, and it only goes one way. So we should see shadow sets behaving differently, especially at beachfront properties and stuff. We should see this phenomenon where the height of the object casting the shadow is dwarfed by the shadow itself. But we don't see that. So that's evidence that our null hypothesis is correct so far. Hasn't been falsified. I know we're kind of I know it's been running a little long, but I'll try and breeze through the rest of this because the intro to the stars thing was I know that's a bit much, but super important because we have to determine what these measurements, like what are they even doing? What are they in reference to? How flat's flat? How curved is curved? What's it in reference to, right? So it's important to establish the history of these things. But moving on now, we're going to look at longitudinal circumpolar orbits and what they should look like. So we've all heard of circumpolar navigation north-south. We've heard some rumors about how this has been done. And how there's satellites that do it, and they go north-south, meaning they go over the North Pole, they go down the South Pole, and they come back up around, meaning they're going around the ball and back over it from the north to the south. Now, east-west navigation isn't a problem on either model, right? Because you can do concentric circles outward from the North Pole on either one, doesn't matter. But this would be a mutually exclusive representation of what they're putting forward. So let's do a quick check to see what these, and because this coordinate system is invariant under transformation, we can actually take all these routes and transform them to an AE map and see if they truly comport to what is a circumpolar route. So this is what it would look like on a ball. Suppose we're at the North Pole, we're coming down the backside here, we're at the South Pole now, and then now we're coming up over the South Pole, heading to the North Pole, and then now we're coming back down, right? So this is what the route should look like. And if you take this on an equirectangular projection, this is what you would see. You would see these two lines, and this is what this would represent. So when you see the spirograph projections of different satellite orbits on an equirectangular projection, and they show you that this is and they're saying like, oh, this is for, XYZ circumpolar route or whatever. This is what these routes should look like when you transform them to an AE map. So we're going up the ball, and now we're going down the backside of the ball, and then now we're going back up the ball, and then now we're going down the backside of the ball. So all of these things represented by this latitude longitude coordinate system should be the same under transformation. So let's take a look at some data sets and see what we got. So we got some spirographs here that represent some satellite orbits, and then flower life pattern. And that's what we're going to get for every single one of these as we go forward for different ones. So instead of a straight line over the coordinate system, which is what it would be if it was going up and going around, what we have are giant figure eights in the sky. So they're coming around, doing big loops, and that's what they're doing. They're not doing they're not coming up and going over around a ball. So again, just more orbits. I'll just breeze through these because they're all the same. Again, figure eights, spirograph, rectangular, figure eights in the sky. Spirograph, figure eights. Spirograph, figure eights, so on and so forth, right? Just never ending. So what about terrestrial? What about boats and planes and stuff? Has anyone ever done it from that perspective? Well, again, let's take a quick recap. East-west, no problem. Done zillions of times a day. North-south, no so far, no satellite orbit has done the correct transformation. Let's look at routes plotted from the famous Pan Am flights, where they were doing their world famous circumnavigation north-south flights. Nope, giant circle. They didn't do it. Same situation with this. This is another Pan Am route. And what they're doing is just doing circles. They're never going up and around a ball at any time. The One More Orbit crew, how about those lads? Did they do it? We'll take a look here and see what they did. Turns out, no. Nope, same situation, just a big loop. Big old circle. And then we have the marketing team, where they were like, hey, the one more orbit lads, these are conceptual images for the orbit of for the orbits. They're not representative of the actual flight plan. It's like, oh, okay, dude. So they took the extra secret polar route. The one they showed us was just the figure eights over the sky or circle or big circles, right? So again, just showing the same thing. No one's ever done this. No one's ever substantiated a circumpolar navigation in the way that would be physically meaningful, to provide evidence for this. It's never been done. There was the one guy who got the Guinness Book of World Records, who flew halfway there and then flew back when he got to Antarctica, and then they gave him the world record anyway. Just like, okay, dude, that's not a real thing. That doesn't count. Why would you do that? Can you not do it? All right, next up. So any questions about that? About these projections and what they represent?
Well, I just make a comment that with this whole 24-hour sun thing, who knows what the actual continents are, and if there's actually a possible still land around us. But if Antarctica is its own continent, then that could be the next thing they have set up to, like, oh, we can go across Antarctica. Now flat Earth is really dead, even though that still means nothing.
Yeah, well, they would have to show us a route, right? And that route would be invariant under transformation, so that would be pretty telling as well. Because no one seems to be going over it. But yeah. All right, so now we'll get into a quick recap of Battle of the Beams. This is another one that was done in the 1940s, where intersecting radar beams from an observer height of rounded up to 665 feet for generosity and uniformity of calculations provided a beam that a plane could fly through at an altitude of 19,000 feet for hundreds of miles, that had to maintain a specific geometry to the beam in order for it to be useful for a pilot to fly through it. So we'll get into the technical specs of what all this means as we continue here. But here's an orthographical view of what the situation at hand looks like. So we got our radar tower over on the right. We have a horizontal beam coming out, and it's going to hit Earth curvature at around 30 to 50 miles, depending on the day. And then we have, and so depending on how you want to internalize how this could work on a globe, we'll go over different scenarios, but this would be like a side view of what's going on here. This would be a top-down view of the beam radiation pattern. So that radar beam, as it's going out horizontally, this would be a top-down view of what we're looking at. The left-hand side of the beam would be dots. The right-hand side would be dashes. So we have like a Morse code, dots and dashes being projected out from overlapping signals. And in the center here, where the dots and dashes overlap, they make a coherent tone. So a plane would be flying through the coherent tone. And that's where the usefulness of this radar system comes into play. So originally, this radar system was used to land planes at night. So it was a blind landing radar system. So what you would do is as you're coming in to land, you'll know if you're off center of the runway based on if you hear dots or dashes in your headset. If you hear a coherent tone, you know you're dead on, and keep going and you're good to go. So what the Germans found was that you could actually boost the signal of this and use a dipole alignment to facilitate the beam pattern, like to make a specific radiation pattern out of it so that you could project the bulk of the strength of it horizontally. And you could fly a plane through this for hundreds of miles. And then you could actually use it to, intersected with another beam at another location using a slightly lower frequency. You could strategically use this to fly a plane at night to a target where you can't judge your distances normally. And when you hit the intersection of the second beam, you will you'll know that you're over target. So that's what they use this system for. And we'll take a look at what that looks like now. So the original system and the measurements that we're going over here were from Stolberg and Cleve, and they were targeting a factory in Derby with the radar system. So that imagine this overlapping beam radar system going out to Derby. And because we know the starting size of the beam and we know what the size was when it was measured, we can determine the angle of the angle between the radar system and the pilot at altitude over target. We can determine how much diffraction there was, how much beam divergence there was, because we know the exact measurements of the equisignal. So we'll get into that as we continue here after we take a quick look at the radar system, just to recap here. So some people will say, I've heard it asserted a couple times, that this radar system could be tilted vertically and aimed at the sky. That's not the case. It's fixed vertically, and it rotates on a horizontal axis on a track. And it uses a dipole alignment. So there's just metal rods, magnetic metal rods that are separated at half wavelengths, so that when the current is run through this tower to produce the radio frequency, the peaks and troughs of that frequency get moved towards the center of the structure and then are sent out horizontally. So what we're looking at here with these red dots along this truss here, this can be tightened or loosened to make a V shape. So you can adjust the equisignal width here. So you can make this overlap, more finely or more widely, essentially based on the distance to your target. So that's how they were adjusting the beam width and controlling everything. They never tilt anything or anything like that. These are all based off of horizontal propagation to focus the bulk of the radiation to the midpoint to be thrusted out horizontally. But to give a top-down view of what that looks like, so imagine these dots here are our dipoles. This V shape is our alignment of the dipoles, and these dots and dashes are the radiation pattern. So this is the frequency that's emitting the beep beep beep, and this is the frequency that's emitting the beep beep beep, right? And this creates this overlapping for our coherent tone. And so this is how you get this pattern from this dipole alignment. So again, just a quick recap of the side view of what we're going to be looking at for the issue here. So the reason that this radar system has a problem with the globe is, one, it's line of sight. So this plane is flying at night at a specific altitude, so that it's flying over, all aerial countermeasures and all that, so that it can't be shot down. So that its likelihood of being shot down is decreased. But that comes at a cost. You can't tell where you're at on the can't tell where you're at when you're flying over target at night. So what they have, what they were using was this radar system to guide them into target. Like I was saying earlier, instead of being guided into land a plane, they're being guided out to a target. So they're flying out over target. And if the beam hits Earth curvature, what's going to happen is you would have diffraction, which is going to cause overlapping signals, and that's going to create pseudo equisignals in the within the beam geometry itself. And that's going to be completely useless by the time you get over target. You're not going to be able to fly hundreds of miles at night through a consistent thing with that. That's just not what's going to happen. So what they, in another case, like let's say that the beam geometry maintains, right, somehow. And then what would happen is this would become sky propagation, and it would be 38,000 feet over target, where the bombers were at 19,000 feet. So this creates an 18,000 foot deficit in the beam geometry, because what was actually measured by the British was the equisignal width was 500 to 600 yards. I'm sorry, 400 to 500 yards wide over the targets, meaning that the angle produced from the starting angle to the to that width over target, there couldn't be any diffraction or anything like that. Otherwise, the system would be much bigger and it would be useless. It would have been like miles big, because that's the whole purpose and why they thought that this system wouldn't work, and why they were safe from it, because they originally ignored the system when they were originally investigating it. But anyway, when we go over the various distances of the targets, just starting from the first target and the measurements that were given to us from the British, what we're finding out quickly is that after 50 miles, this system it just doesn't work on a globe. And the only way that it does work is if the beam is propagated horizontally over a plane and a plane is flying over the plane. In that radar signal. So and real quick, the altitudes that these were used for during the bombing campaign that lasted a year by the Germans. We have the Telefunken company who did the technical specs that set up the radar system, and when they tested it, they flew at 13,000 feet at different times of the year, so different refractive conditions in the summer and the winter, and they found that the system worked up to 1,000 kilometers. Or that it was usable within 1,000 kilometers, and they give their beam divergence. It was sub 1 degree for the beam divergence. So over target, that equisignal at 500 miles, at 400 miles being, roughly 600 yards. They're saying that up to 600 miles, it would be like, 800 or 900 yards wide. It would still be useful. So they were still using it, all throughout the year. And we have some very specific angles for that beam geometry. So if we take the arctan, which is the angle from the radar system to the pilot, which is what I showed in this picture up here, if we take that angle, that's also sub 1 degree for the altitude over the target for the distance. So when we get into all these, we're looking at sub 1 degree of difference here. And when we look at the beam geometry, we don't have a distance axis on this projection here, but what we do have is at some point the beam will be 3 degrees in the sky, which would be around like the sky propagation range or whatever, right? So we don't know at what distance exactly this beam would be that high in the sky. But what we do know is that over target, based off of these angles, we would be way back here in this range where the beam is just going over the plane, right? Over an actual plane. So at no point is anything being obscured by curvature. This was never accounted for. This actually operates in the face of curvature. It's never been explicitly stated how this could work in terms of refraction or diffraction. No one's put any numbers forward to explain anything. If you try to use refraction to make this line of sight, you would have to invoke 2 different refractive indexes that no one has ever observed to basically extend the Earth's radius to 15,000 and 19,000 miles respectively, depending on the distances. And then the distance and then at the target, somehow these 2 extreme refractive conditions would have to overlap such that it compensates so that the both intersecting beams can be at the same altitude, even though their distances are different. It gets preposterous. So like, that's not tenable. And then for diffraction, if it hits Earth curve, the beam geometry is ruined. You can no longer adjust the equisignal afterwards. It loses all viability. And in that regard as well, what would happen, like I was saying, that pseudo equisignals would be produced because of the beams diffracting and expanding out. Well, what would happen? Part of the countermeasures that the British used were actually just sending out their own horizontal signals as well of the same frequency, and that would create pseudo equisignals. So this system was just as was super sensitive to interference like that. So in other words, the only way this works is if from line of sight from radar to tower or from radar to target, there's no obstructions or interference or anything like that, because otherwise the system would be off. It wouldn't work. So before we move on to Cell and Ellie's, any comments or questions?
Do the pilots have to be flying in that beam with the 3 lines the entire time when they're heading to the destination?
Yes.
Yes. Okay.
And
And
could
then when the
could
2 beams intersect, they
deflection
know when to drop the bomb?
Yep.
Question.
also
Hello?
could deflection work as a reason that it goes over the curvature?
Deflection, no. So if it deflects, it has to follow a tangent to the sky from that point, which would put it, miles or, thousands of feet above, useful geometry. Because the thing that makes it useful is that equisignal, right? Like the distance of this beam can be like that radiation pattern as it expands outward can get pretty big. But the important part is that it never diffracts or like bounces back and interferes with that equisignal.
Cool, thanks. Yeah, I was hearing people claim that deflection answered it, and I didn't think so either.
No, dude. Because you think about it like this, right? When we're talking optical observations, and there's a sagitta, right? They're like, this is that point of Earth curvature that has to be overcome before you're starting to come around the other side of the ball, right? So think about our radar system, this overlapping beam geometry, right? That started out at 30 meters, right? In width, and then it's going to hit Earth curvature here. It's done. It's done. The whole thing is done, right? And then it doesn't start diffracting around the ball until after it gets past that midpoint. So like this idea that this hits Earth curvature over all the miles in between the sagitta and the source, and then it overcomes that and maintains the geometry on the back end, is just ridiculous.
Yeah, diffraction does not answer this. Okay, I just wanted to make sure.
Yep. Yeah, it's completely untenable. Like the whole purpose of this dipole was to adjust the equisignal. You can't do that if you hit Earth curvature. That's a wrap. So your system would only be effective in this range. You could only take it to 50 miles. 30 to 50 miles would be your effective range if Earth curve were a factor. That's all this would be effective. This is all you could do. You could adjust the signal to 50 miles. That'd be useless.
Nice. Thanks for clearing that up. No diffraction.
None.
Hey, Alan.
Yo.
You made some hints throughout your presentation about map projections that were used by the state or by the government to kind of manufacture consent or confuse the populace to think maybe the enemy was something or something of that sort. Do you have any examples of these ones?
Yeah, I don't know the specific names off the top of my head, but I'll link you the video. You can watch it. It was like the various projections they would show at different times of like war. Like during the Cold War, they would show a projection where Russia looks huge and all that kind of stuff. I'll get you the video real quick. You can check it out.
Perfect. Yeah, if you could definitely relay that, because I don't know, that in itself is a very powerful concept. And again, Alan, you're an asset to the community. We really appreciate everything you do.
Yep, no worries, lad. There's another video too called what was it? Something about maps and propaganda. That's a really good, really decent video that kind of shows the same thing about how you can make, different countries look irrelevant and stuff. So there's a couple of videos out there on the subject as well. Was someone about to ask something?
Yeah. So Alan, I have the only possible refutation of the Battle of the Beams that can actually work.
Go on.
Which is all of this information essentially came from the British government, right?
Nope.
After the war.
Nope.
That is the sourcing of it.
Nope. There's a ton of it that's from German documentation as well.
Okay. So German documentation and English documentation. The only possible refutation is that they lied about things that went on in World War II. And, you know, somehow they lied about something that happened to just prove flat Earth. It's not a very tenable position to have, but it's the only one that could actually refute it, is that they just lied.
Yeah, so the radar system was used for an entire bombing campaign, though. So I don't know.
Yeah, I'm not saying that this is actually what I believe, but this is the only possible refutation, is that...
Is it possible if it's like retarded, though?
Yeah.
Yeah, when you first pointed this out, you were saying how retarded it was, but how funny it is that no baller would take that position because they'd have to doubt the interpretation of history and all that.
No, the actual best refutation of it, real talk, was Tim Pool said that the Germans ate special GMO characters that gave them night vision.
True.
That makes sense.
And I think that's the much stronger position.
Yeah. But
All right.
No Globers could use that argumentation, because to doubt what the British and Germans said about the war would obviously have clear implications.
Yeah, I mean, they go over the whole narrative too, because like, here's the thing, right? And the historical documentation and everything, and obviously everything that's written about it is going to be approved by the Crown and all that. But in all the instances where they talk about it, they get super vague around a mechanism for it. They never say, this is explained by diffraction, this is explained by refraction, this is explained by ionospheric bouncing or something like that, right? They get super vague around that, and they just loosely reference a guy named, can't remember his name off the top of my head, but they reference this guy's calculations, and they're like, this guy calculated it, but they don't say what he calculated or any values or anything, right? And then they tell the story that that guy withdrew his calculations and was like, yeah, this would never work because this is not how a line of sight system would function with this. And
yeah. So here's an actual question. Do you think that they released all of this information approved by the Crown, not knowing that it inadvertently proved no curvature?
Yeah. Yeah, they strategically, yeah. So check this out. In the documentary, R.V. Jones goes over his estimation for the angle of the beam, of the width of the beam, right? And the estimation that he gives, he did plane trigonometry to do the estimation, because we did the same estimations and got the same angles. So, but they don't tell you how he did, what estimations he did. They just talk about the figure, and then they don't go any further or anything like that. They talk about it in such a way that it's like ambiguous or whatever. But when you plug it in, you only get this from plane trig, and you only get that accuracy from that. But the way that they talk about it is like this. They make it seem like that guy that did those calculations, who withdrew them, they make it seem like he was right all along, but they never reference his calculations or tell how.
I see.
That's how they get away with it. But then when you go over, like I said, when you do R.V. Jones's estimation that he gives, and you do ours, well, the only way you could get that is if you do plane trig. So he knew what was up, but they had to deliver this narrative and be heroes, right? Because this system was crazy. A lot of people died. They were able to do successful targets with this, constantly. Way more accurate and effective than what the Brits were doing, which was just blind cell nav at night. So like that was like pretty much DS. It wasn't working at all. And yeah, like they had to tell this like story about how they overcame this. And yeah, when you get into the details of it, it definitely lends itself to a plane, but they tell it like ambiguously so that they can leave it to make it seem like, yeah, they solved how it worked on a ball. But they never did or talk about it. Okay. All right. So next up, we have selenilian eclipses, which is said to be an eclipse where the Earth is casting a shadow on the moon, because it's in between the sun and the moon. Yet this phenomenon happens when the sun and the moon are well above the horizon, and in some cases, as far as 4 to 5 moon diameters above the horizon. And what's stated, like the mechanism for how this works, is that because the sun and the moon are apparent objects in the sky, the eclipse has happened, already due to the physicality of the bodies, but we're seeing the refracted version of it coming up over the horizon, and that's what's producing this effect. Now that could be a possible explanation for the mechanism, but what happens is that the shadow sometimes comes top down instead of bottom up. And what's never been predicted, and at least not consecutively predicted, is during a Selenian eclipse, will the shadow be top down or bottom up? Mechanistically, there's no explanation for how it goes up, or goes from top down to, from top to bottom. So this is what should be seen on a eclipse if the geometry is such as the assertion of mainstream heliocentrism and globularity. But what we actually see sometimes is that they're top down. They're not always the same. And because the shadow direction isn't in the predictions, what I take this to mean is that the assertion of the Earth being the causal mechanism in between these two bodies, due to, as we rotate away from one body into the other, I don't think that that's the causal mechanism. I think that's pretty apparent that a celestial phenomenon like this occurring above the horizon is just a celestial phenomenon occurring above the horizon. And to assert refraction as the causal mechanism as to why we can see it is just making the globular position equivalent to our position, which doesn't add any mutual exclusivity for them. Now, when we get to the shadow, though, that's where we diverge in explanations for mechanisms. So I have a couple of videos. Actually, I didn't add the recent ones, but there's some really cool Selenian eclipse videos on YouTube that we just seen recently, where they say that refraction's occurring, and it's like, okay, if that's the case, then it should only be like maybe 1 moon diameter above the horizon. But we have some videos where it's like 3 to 4 above the horizon, which is at that point it's just like, all right, dude, what are we doing here?
Yeah. So I do have a quick kind of question on that. The live stream 1 text, I linked a diagram which is commonly used to sort of explain it, and I already have a good idea of what the reason for why this wouldn't be true is, but this would be good to go over, as this is the common explanation for why the shadow is on the wrong side, the one that is invoked, at least.
All to explain why it's on the wrong side.
Yeah, I linked in live stream 1 text a diagram.
Got it up. Okay. So, light source way beneath the ball, object way beneath the ball, yet we're seeing it up here. Like they have to geometrically have it up here, but have everything occurring basically wrapping underneath the ball, and then you're seeing it on the top side of it. Like, this is preposterous. And then not only that, right? Because it's not even that you're seeing it from this angle looking downwards up. You're actually looking in this direction at the thing in the sky above your horizon. So for this to be mechanistically occurring literally on the other side of the ball underneath you, and then be completely on the opposite side above you, 3 to 4 or 5 moon diameters in the sky. I mean, that's like, you're now entering the realm of unfalsifiable insanity.
Yeah, because they're playing around with scales in a way to where it's not analogous at all.
Not analogous at all, and it's showing you as if you're looking down at it from this direction from it. That's not what's happening. Yeah.
And you're also so much higher up than the highest mountain.
Yep. Got to make it non-analogous to get it to work. Or, to give it the perception of working. All right, so next up we have the 24-hour sun observation. Now, the sentiment of most flat earthers in the community, from my perspective, was that the sun, that objects in the sky do not prove the shape of the ground. And my position was that while that's true, that you could make it like that the Gleason's model in reference to how you would see the sun and there being no 24-hour sun in Antarctica, I thought that perception of it was correct, and that's how I would have argued it, and I have no problem admitting to that or talking about that now. I was completely wrong about that. But the sentiment from most of the community was that wasn't even applicable, and that like my position was like low key retarded, and like I shouldn't commit to a model. Which, you know, in hindsight, it was like, oh yeah, good call on that. You know, there was a lot of hubris there, in it. So what is explained by this in the globe model is essentially by the curvature of the Earth. So earlier we went over different instances where Earth's curvature was asserted and to have like an outcome that was going to be different, right? And for all instances up until now, we have no instances where Earth curvature would provide an observable phenomenon that's physically different, right? So when we examine the differences here, right? We're like, okay, since all celestial phenomenon is occurring above the horizon, et cetera, it's never been substantiated that there's physical Earth curvature due to shadow sets, due to radio horizons being blocked, physical Earth curvature measurements, et cetera, right? We have this one instance, right, where it's like, is the conceptualization of the Earth being a plane wrong, or is how we conceptualized like an explanatory model of how it would work wrong, right? And I'll give my personal speculation on like a mechanism of how this could work or whatever. But this would be the one observation that was put forward, that the simplest explanation is that, well, it's just due to the Earth being like the Earth curvature that we couldn't find before. It was there the whole time, and it's right here now in this observation. So what I would put forward mechanistically, right, is what we've already been over, is I've established that you see in a dome, in a hemispherical dome, everything you see in the sky is apparent and personal to you. So what I would argue, well, what I would put forward is that in the northern hemisphere, where's my star fields? Is that in the northern hemisphere, you're seeing two star fields at the equator, one diverging to the north, one diverging to the south. And then you have your dome of vision, your limits of vision. And when you're in those hemispheres, everything is going around you. And to facilitate that prospectively, everything wraps around your dome of vision accordingly. And in the north, on an AE map, that makes sense. There's no contradiction there. But as you get to the south, you would expect to see things like you would expect to be looking north from the south, and you would expect to see the sun in front of you and not set. You would expect to see the phenomenon behave differently in that regard. But what actually happens is everything is still perceived around you in completing your dome of vision, completing that perspective, such that you don't see that when the sun is coming to your local solar noon, when you're in the south, you don't see it follow the same arc. It starts to antarc, and that's just completing your hemispherical dome of vision. So mechanistically, I would say that this is just due to like this is just an optical phenomenon completed by your dome of vision. And I don't think in my version of cosmology, right, because some people believe that there's things beyond Antarctica, outer lands, etc. I think that this is the edge of everything, and that as you get out here, you still have your depth of vision, that field of vision. So you're going to perceive all celestial phenomenon around you in such a way that you can always get back to the north. You can always get back to the center, and you're always going to perceive it as from the point of view that you're in the center of it. Whereas the previous prediction was that you would be following the sun, so to speak. So you would see the sun arc across and set, if the old conceptualization were what was true, but that would mean that you're not at the center point of the creation. So that would be like kind of contradictory in terms of like and how I view the cosmology of it. So that's just my personal explanation for it. But yeah, so we have the one instance where there was a mutually exclusive phenomenon provided there mechanistically, assuming no other mechanisms other than optical curvature.
That's assuming the outer ponders didn't pay you off to say that, right?
And that's assuming that the outer ponders have me in their pocket. Yes.
Yeah. Okay, cool.
All right, cool. That is the null hypothesis for flat Earth. So to quickly recap, we have, let's see, measurements of Earth being independent. Measurements of Earth curvature being independent of celestial phenomenon versus being dependent on them. And it turns out that they're dependent on them, and that in most cases, they actually make measurements that are sub 180 degrees. And it isn't until after referencing the stars and through several corrections and assumptions that they can get measurements that comport to over 180 degrees. We have geometric differences in shadow sets. We have geometric differences in radio propagation for line of sight. We have optical differences in true positions versus apparent for a celestial phenomenon in particular, where everything is personal. I would argue everything is personal to us. Otherwise, we would see each other's sunset beams, etc. Right? But we don't. They're all personal to us. Everything is mapped out as if it's personal to us, although all sky phenomenon has different distances that can be extrapolated under different phenomena or under different mechanisms. Although distances in the sky in terms of like orbital radius, etc., can be extrapolated as a function of the periodicity of the object in the sky, it doesn't appear to have any physical meaning, as all celestial bodies can be mapped to a celestial sphere and an equidistant web with a radius, with a length of 6218. So with that said, I don't see enough evidence to throw out the null hypothesis that the Earth is planar over one observation. While it is interesting, right? There have been several people that have put forward models to try and mechanistically explain this. Now, whether or not those models are accurate or are going to hold true or whatnot, we're still early in figuring out this phenomenon because there was such an air of deception around it, especially in regards to the research station that was deleting 8 hours of footage every month or every day. That was just like insane. And then a couple instances where the footage was admitted to be edited so that they could make it look better. And at that point, we were just like, is this phenomenon even real or not? So, I don't think there's a reason to panic or freak out or feel like you have to immediately explain it. These people had like 400 plus years to figure this out, make a model, add corrections, come up with stories for the corrections, adjust their theodolites, tell us why they're adjusting it, So like, I think we're being really critical and demanding like instant satisfaction and gratification. And there's just a lot tied up in that. And that's not the way any of this works, man. This conversation is going to be ongoing and continuous. And I think that getting caught up on one specific thing and, throwing everything out and is a mistake, and we should really work together to figure this out.
So with that map you had with I don't even know what to say it is. Had the north and the south like spiraling.
Yeah, that was E1's map that I've posted many times. That got for Alan got. He wasn't supporting that idea though. By the way, I don't think he was just saying that it's not tenable in his.
Are you talking about this one?
Yeah, because because in Australia, I see I've time lapsed the Southern Star rotation. So, but the guy in Africa can also. So, is like the whole thing turning, or is it moving due to your location? Like a rainbow, or
It's with 2 star systems. That's showing 2 star systems there.
Yeah,
that's what E1 thought.
Yeah, I think it goes to like the same location or whatever perspective wise. But this was in specific reference to just being like a top down version of this. So like this would be bottom up looking at the 2 star fields, and then this would just be top down.
All right, it's just because I'm looking south and I see it where in Australia, where that's that's a little bit like southwest or something. Like,
yep.
So I'm just.
Oh, he also has Antarctica as its own continent there at the bottom. I don't know if you think that's Australia, but that's Antarctica at the bottom. So it's just a different continent makeup that he was convinced that must be the case, and that 1 star rotation wasn't. I'm going to get him on here someday.
Nice. But yeah, that was just in reference to the 2 star fields diverging at the equator. Because if you look at it, they'll say, okay, the ball, the map, everything, heliocentrism is all predicated on incoming parallel light rays, and then you only see a deviation based on the contour of the Earth. But at the equator, you see these 2 divergent fields, and they're like, okay, well, that's where perspective comes into play. So we can have perspective at the equator, but anywhere else, it's due to physical Earth curvature. So like I'm taking the position that at the equator, the reason that these diverge like this is because this is actually representative of 2 star fields, and then we have our dome of vision that we see, that we perceive these star fields in.
Yeah, Southern Stars just still get me.
Yeah, well, there's a video here if you've ever seen what's his name, No Fanfare. He has a little model here where he gets in the dome with the camera and shows the counter rotation with a dome effect. So like,
within a dome.
It's not a dome within a dome, just a dome there. Want to see it? Play it out.
Yeah, I see. I've just seen other people like dome within a dome. And...
Yeah. All right, we'll play it out here. I'm going to go AFK for a second. I got to run to the bathroom.
What exactly was it that you were saying about the star rotation, and was it the continents the way they were or something like that?
Yeah, just that model.
The finished product.
Because
I did a couple extra things that I didn't show on the
I'm
making.
double check because I have filmed.
Put a little Australia there.
The Southern Star rotation.
Oh, 1 second. There's audio with this. I'll share the audio. Give me 1 second.
Next time I do it, I need to get my compass out and like determine if I am like looking dead south while I'm looking at the Southern Star rotation.
And Africa over there.
All right, can you guys hear the audio?
The phone's going to go into that.
Yeah, we can hear the audio.
All right, cool. All right, I'll be back in a few.
And the phone will be recording, and then we'll be able to pinpoint that that's Australia, and over here is Africa. Yeah, there's a lot of people saying that the FA model don't work. Well, let's have a look. I've got a couple of tin cans to prop that up. Yeah, let's go and have a look. There's Australia over there, in Australia, on the map, on the flat Earth disc. There's Africa. Lined up with Africa.
Looking on your flat Earth map, we stand in South Africa and looked south and saw Sigma Octans and the constellation Octans in the south. Then we went to South America and looked in the south and saw again the same constellation and the same star on the same place, a little bit higher, but horizon. And in South Australia, exactly the same. And now's my question: how can we see the same stars and the same constellations in the south on the flat Earth? We are looking in 3 different directions.
Okay, guys, we're in Coffs Harbour here at the moment. Latitude 3017, blah blah blah, Coffs Harbour, there, New South Wales, Australia. And I'm choosing the date. Equinox this year, equinox again, 3 a.m. in the morning. Okay, so that's the Coffs Harbour region. Pointers are down here underneath. Take away the ground, and there they are. Right, now, I want to go over now to, wrong place. I'll choose another place, roughly same latitude, over here on the east coast of Africa. A little place called Scottsburg. I'll click on that. And there's the crux, Southern Cross position, over there. So when I'm at Coffs Harbour, 3 a.m. in the morning on that day, Southern Cross will be over here. And in Africa at Scottsburg, South Africa, Southern Cross will be here. Right, I'm going to clap my hands to so I can sync the camera video and the phone video. I've got the phone going, and I don't want to make a real big file on that because it could be whatever. Here we go, 1, 2, 3, clap. Alright, we'll use that spike in the sound to sync the two videos together. Now you can see in the phone how it's reflecting off the side of the wall of the salad bowl. Alright, just move the stars, there goes the terminator line, see the stars moving around in the reflection. Alright, there's the lights up there. So that's the lights on the reflection. Right, I'm just going to move this around here, because I just want to try and show you what happens. Now watch those stars on the phone. I'll see if I can, if I zoom in anymore as I spin the geolocation. Now I'm going to spin the geolocator around, and you watch the stars in the phone. See, they turn. The stars are still, but the geolocation. We're moving the geolocation, and the stars are rotating. Right, I'm going to hit Australia there, and the west coast is actually the east coast. I've got Australia over there, stuck to the model, so you can recognise it, but the way the thing spins around, clockwise here, it's going to come to the west coast first, so the west coast is like the east coast, but I can't have the map down here, I have to have that there, so that's representing where Australia is. Right, so if we notice where that little green star is, which we'll show on the phone later because these videos are going to be synced. Come on. So we've got green at the bottom left, orange in the middle, and crimson one at the top right. I had to get crimson because I couldn't get red. I wanted to make a traffic light colour scenario because it's pretty universal in colours. The other one, if you go back anti-clockwise, after the green you've got blue, and then there's a yellow one. And then blue again. I'll just arrange them in this way so we can distinguish the stars. Alright. Now move the camera back over here. I'll unzoom. Right. Just got to get it out of the way because I'll end up knocking the camera over, the T900, concentrating on doing something else. Right, so now we're going to move that terminator line around South Africa. Right, that's South Africa. We'll go back to Australia. Now, we want to have a look at the position of that green star. Oh, I forgot to say that green star is representing the Southern Cross. That is the position of the Southern Cross, the green star. Okay, I'll establish that now. So the bottom left-hand corner, just above and to the left of the blue part, Western Australia. Right, now what I want to do now is I'm going to move the geolocation. Okay? I'll move the geolocation and the stars will stay still. Well, they won't stay still on the freaking camera. Alright, I better move it over here. Right, so I'm going to move the position of the geolocation now. Right, so now we're not talking about times and time zones here right now. I'm talking about a moment. If I was on the phone there in Australia with someone in South Africa, that is the moment, that's not a time zone. So if I could say to someone, where's the Southern Cross right now? Over where you are. Right, so this is what this is going to do. When they spin around, the Southern Stars, when they're still, and you spin around your geolocation, clockwise, then the stars go anti-clockwise. Alright, so there's Africa, we'll get the west coast of Africa around about the middle. There, and the green star now is over on the right hand side. So, alright, that's where that is. Back to Australia with the geolocation. West coast of Australia, we'll put that in the middle. Green star bottom left, geolocator again, back around South Africa. Get the west coast of South Africa around about the middle of the screen. I've got to keep walking around this camera. Damn it. I've got enough room to swing cat in this place. It's very hard doing this. I should have seen how it went trying to make model in here. Alright, I think that'll just about do it. That's enough proof, I think.
That's crazy. Yeah, because I never knew the Southern Cross was in like a slightly different position from Australia.
Yeah, that kind of doesn't work already. Even if it's where where it's supposed to be, it's not where it's supposed to be. Is what I mean.
Yeah, it's one of not a professor's Dave's favorite arguments.
I hope somebody can post this video in the chat.
It was, if you scroll a bit.
Yeah,
Thank you.
That's what I've thought all along. There's like some kind of rainbow effect, like things are moving based on the observer.
Yeah, along with the dome effect. Yeah.
Yeah, something.
People tend to deny rainbows.
But does someone have like because that's the southern. Does anyone have like the whole thing, like the north? You know, the north, the middle, the south.
Well, the north works like we see it pretty much. It's the south that's the problem.
But that's the thing, is the north and the south a mirror? Because he had his lights in the north and it was mirroring in the south. But that's what we don't. I don't know. Are the stars? You know what I'm trying to say?
He's got a couple other videos in that series on his channel, as well as a left-right comparison of the north and the south, showing areas where it could be due to the spreading out of the dome effect that makes them look like different constellations, when they may just be a reflection of the other constellations.
They would be like reflected and like flipped and stretched out. That's why people think they don't line up, because people will line up some and then it'll like the other ones look all off. Like nobody says it has ever been able to show it or whatever, but like that's how it would be speculated to work.
But what about that? The Southern Star Cross thing? Like, is there something like that in the north that's kind of close to that or something?
What do you mean?
No, is
Well,
the
it's supposed to be the opposite of the North Star, right? So that would be where the North Star, but it doesn't even align. So that the ball is dead right there when you think about
it. Yeah, I'm not super up to date on my Southern Cross argumentation.
The Southern Cross is not at the center. It's a fair way out, same as the one you have in the north. So it goes upside down. It goes around in a circle. That's why it changes sides of the sky. The Sigma Octantis is the center, near the center, not the Southern Cross. Southern Cross is like the Big Dipper.
Yeah, I'm just saying, if it's a mirror, shouldn't the Southern Cross kind of be in the northern bit?
Yeah, but it isn't.
It's not a mirror, because Orion's belt is in the southern half and there's no northern bit. It's right on the celestial equator. It's.
But Trouble, have you heard the argument that it doesn't align where it should be if it was?
No, I don't. I just told you why. I just told you why. It's not in the center. So I can get up, and if it's on the left-hand side, the cross is on its side. It can go then up to the top, and it's vertical. Then it goes over to the right. It's on its side again. Then it can keep going around. It's upside down now. So if you're comparing one side of the sky to the other, like if the cross is in a different place, if it's moved across the sky, do you get what I mean?
Not really. I'd have to see a visual of it. I think the claim is that it should be exactly the opposite of the North Star if it was a ball, is what I was saying.
No.
And they're saying it doesn't. It doesn't actually fall where it should.
But that's Polaris and Sigma Octantis. That's not the Southern Cross.
So the Southern Cross is perfectly where it should be for a ball. Is that what you're saying?
Yes.
Yeah.
Okay, I didn't know that. I didn't know if that was the claim. If it was about
No, it gets confusing because yes, that's exactly what's happening. Some people will think that, or they think that they're the same or whatever. But yeah. All right, so that was the Prezi. Any questions, comments, or concerns?
Wait, So as he showed Australia where the Southern Star would be. He showed Africa where the Southern Cross. What about South America?
What?
Where would it be?
Well, it would be their daytime, so they wouldn't see it. We can't all three see it at the same time. But
Oh, right.
and I think they were doing
The,
the same time. I'm not sure.
no,
Or
that
when it
is,
does go nighttime,
yeah.
what does it do? That's I know.
What did the other ones
He
do?
might have details on his channel. You should maybe go to his channel.
Yeah.
It was kind of hard to hear what he was saying with the 2x speed and the accent for me.
Oh, was it? My
It
bad.
goes around in a circle, just like we're seeing it. Like the whole thing doesn't move across the sky. The whole celestial pole isn't moving.
What's
It
his
just goes
YouTube?
around in a circle. That's all.
What's his YouTube?
Oh, no fanfare. I linked it in the main chat at 12:04 past the hour. It's got a
So no reputations to Battle of the Beams yet. You put the word out. You've had people
no.
make a
So
few bad attempts.
Cass took a crack at it and came up with basically like oceanospheric induction, which was me saying that essentially using the ocean as like an ideal conductor, the signal would hit the surface of the ocean, propagate a little further, like basically just kind of boosting itself along, and then somehow like that would like honestly, it's not a great explanation because the beam altitude is 19,000 feet, so I'm not exactly sure how that was supposed to help, but that was one possibility that was put forward. So in other words, no, none.
Yeah, and I've heard Ruhif saying that diffraction's it. That's the answer, and then somebody else was saying
So
that beforehand.
so the fraction would have to be like the explanation because there's really no other way to do it. But if you diffract, like you ruin the beam geometry and it's over. So it's like your only way to win the game is to not play.
Right, and that's like a no play.
Yeah, just to baselessly assert it and never talk about it or put any numbers to it.
Yeah.
So yeah, like our librarian, like he was saying, at this point you would have to do like a physical demonstration to actually provide actual refutation to Battle of the Beams, which is like no one's going to be able to like, recreate that or do that shit. So I'm not going to put that on anyone, but yeah, it's a precarious situation.
Got to keep that curvature somehow.
Yep.
Good job, Alan. I don't know if there's any ballers in here want to refute or ask questions, or anybody have any questions?
I'm just trying to think what they would say. You're an idiot.
Nah. They would say, wow, that's a really well thought out position. And I look forward to building my own null hypothesis presentation. And then we could do back and forth and have future discussions where we go over, mutually exclusive evidence and try to get to the bottom of the situation. I think that's what they would say.
Nah.
West Coast versus East Coast? Is that what you're talking about?
What's that?
That's being very
West
generous.
Coast versus East Coast? No hypothesis throwdown?
Yes. Yep. East Coast, West Coast,
They
no
would
hypothesis battle.
I would say, where's the dome?
Where's the
Dude,
dome? Well,
is Liliana
I don't
here?
think anyone has like. What's that?
Is Liliana here?
Looks like she is.
think she might be making coffee if she's not.
Oh yeah, you know what? I thought I smelled some brush tail in the back. brewing.
We can
So
all smell it.
yeah,
That's the thing about brush tails. It's so delicious, brush tail coffee, that as soon as you take a sip, you're always smelling it because you're just so addicted to how good it is. But there's no withdrawal effects. So
you know,
get yours today at what's that site again, Alan?
oh, it's brushtail.coffee. But you know what's really interesting about brushtail coffee is you know how people wear deodorant.
Yes.
So I found that if you just rub brushtail coffee on you, that's just as good, and if not better, because it doesn't have aluminum in it, and you
The
smell
reason they
great.
call it brush tail is because
Smell
you
great.
can brush your teeth with it.
Yep.
And your tail. And your tail, I heard.
Yep.
Yes.
All right, lads and ladettes, that concludes the Prezi. I'm gonna close out the stream, but I'll hang around for a couple minutes, see if anyone has any after stream thoughts or something like that. I'll be back in a few. Yo, shout out to the boys holding it down in the chat. I see you out there, Glenda and Clit Rub, your boy Clit Rubs, and my boy Leland out there supporting. Thank you guys very much. Much appreciated. Hope you guys enjoyed the Prezi. We will see you guys on Tuesday, where we're going to have Gregory do a little Prezi on, what do you call, debate tactics and formal logic. So our boy Galatrax, aka, who definitely isn't Bruce McGuire. I'm winking. You guys can't see, but I'm doing a lot of winking. Galatrax has been crushing it in the logic and analysis department. And he said that Gregory was, teaching him everything and had a lot to offer. So Gregory is going to do a Prezi on logic, and we're going to learn about logic fallacies and debate tactics from our boy Gregory. Shout out to him. We'll see him Tuesday, 8 p.m. Eastern. And then we have possibly the return of research and reading night. I don't know, on Thursday, but if not, we'll return with Flat Earth Fridays. And maybe we'll do something sporadic in the week and hold down a Twitter space. So we'll see what's up with that. All right, guys. Catch you on the next episode. Oh, and if you're not on the Discord, by the way, guys are slacking. Here's a link to the Discord.